my talk is titled as a question, which is in itself is a vague question. Can a heavy quark act as a Brownian particle? Now I will clear off any. So I will tell what specific setting does we look at when we ask this question. But since the phenomena of Brownian motion is seemingly classical and also quite simple, so this is an interesting question to ask, whether a particle which we usually associate with quantum phenomena, can it show a Brownian type motion. So first of all, just to brush up on some basics of Brownian motion. So how did we first know about it? So even before Robert Brown, there were people who have mentioned this kind of motion in solutions. So some kind of a heavy particle immersed in a solution, and then studying its motion, and they saw that there was some jittery motion which was happening due to collisions with the molecules, collisions with the constituents of the solution. But Brown was the first one to actually write it up in some kind of article. So he showed that a pollen grain immersed inside water solution moves in a jittery way via collisions with these water molecules. He didn't mention molecules, which was later actually given. So Einstein gave a theory for this kind of molecular motion through thermal agitations. And what he said was that pollen particles were actually hit by individual water molecules, and that gave rise to this jittery motion. And in 1908, what Perrin did was experimentally verify this kind of a molecular Brownian motion model, because he calculated the value of the Avogadro's constant, which actually gives the number of molecular entities inside 1 mole of some substance. And from there you can get the size of the molecules, which essentially tells you that the fundamental entities that are giving us this motion are actually molecules, not some larger entities. Now this is one example, one simulation which shows such kind of a motion. So this yellow particle is the big particle which you can assume to be a pollen particle, and these are the water molecules, let's say, and they're being bombarded onto this particle at some random instant of time, and then it moves through this solution in some jittery fashion, where the trajectory here you can see by these blue lines. Now once you take a look at this picture, the first question that you ask is, this doesn't look predictable at all. So what essentially you can say about the motion of the particle. So what Einstein did was essentially calculate the average position squared of this particle. So basically how far it has moved after a certain amount of time, and that can actually be predicted using some probabilistic models, and that is a big surprise if you just look at this jittery motion in itself. So what you can say is, on an average you can say how the particle will move, but individual trajectories will be significantly different because of this random hitting of these molecules on the particle. Now this is also one interesting picture. This was drawn by Perrin in his book Les Atomes, where he was doing an experiment with some micromolecule, and what he has plotted is actual position of a micromolecule after some 30 seconds, and these dots represent actual experimental positions of the molecule, and you can see some random motion is going on there, and then you can predict the distance using Einstein's molecular theory. Now so this I have already said. So essentially it's a random motion of a particle immersed in a medium, which is generated by random fluctuations so essentially there are random fluctuations in the particle's position due to the random kicks it gets from the medium particles, and as well as momentum. Now since there are so many collisions going on in essentially 10 to the power 14 per second, so you can't really model it in terms of a mechanical problem of 10 to the power 14 collisions, or some dynamical problem which contains all the molecules and the pollen grain of the system. So what you can do is you can give some probabilistic model which turns out to be quite similar to a random walk problem, and which gives us the average behavior of the system over after some time. Now some examples of Brownian motion. So this is the obvious one which Brown first figured out, and the other one is also quite in a daily life example. So dust or pollutant particles in the air, they also behave like Brownian particles. And one example which is related to astronomy is stars' motion within galaxies, because stars are gravitationally attracted by various kinds of bodies in a galaxy. So there also they exhibit some kind of a Brownian motion through this medium. The last one is what we are asking, whether a heavy quark kicked around by gluons in a heavy ion collision. So all these things I will explain. Can this be explained by Brownian motions? Now, what are heavy ion collisions? So essentially, when we want to study the subatomic structure of the universe, so what we do is we collide heavy ions, and then we study the products of after the collision, whatever we get, and then we want to predict whatever is happening inside, which is causing this kind of yield essentially at the end stage. So here this has been given. This represents one evolution of the system. So essentially there are some colliding nuclei initially, then there are some strong fields that are generated, and then there are some quasi-particles which are just particles with some different properties, and then it reaches equilibrium, and then it hydrodynamizes, and then you get some particles at the end of the experiment. So what we are studying the system is in this stage where there are strong fields, and we want to study how a quark is moving through these strong fields essentially. Now why do we use heavy quarks as a probe in such kind of collisions? So this has been proven that they are produced in very early stages of collisions through perturbative processes. So most of them are produced very, very early, and they are alive and kicking through the whole evolution of the medium. So essentially they are spectators of the whole evolution of the system. So they are affected by different stages of system in some different ways, and then you can from their dynamics you can predict what is happening inside the medium as you detect them at the end stage. And since they are not too copious, so if there are too many of them, we can't really track them. So, and heavy quarks are very less in number, so we can actually track them. And also their number doesn't change because they're only produced in the initial stages, so they are quite easy to track. Now, which quarks do you consider as heavy? So these are 3 generations of quarks, and these are masses of these quarks. Now, which one of them do you consider to be heavy? So one criteria is that the particles which have mass more than the typical mass energy scale of the system, you can consider them to be heavy. In case of heavy ion collisions, it is of the order of 1 GeV. So here you can see that charm, top and bottom have masses which are approximately 1 GeV or greater than 1 GeV. So naively we'll assume that charm, bottom and top are the ones which we should be focusing on. But usually top is not considered because there are not enough of them to be able to track, because they are very, very, very high masses. Now the question is, how do we simulate the quarks and gluons motion as they are? So initially you have some gluons here, and then quarks are moving through this medium. How do you simulate this dynamics? So since gluons are huge in numbers, this has been proven that you can treat them classically, and their dynamics is exactly similar to what we see in Maxwell's electrodynamics, but for what are called color charges. So this is another kind of charge which is different than the electromagnetic charges that electrons have. So the dynamics is a bit more complicated, but it's essentially the same as the classical Maxwell electrodynamics for electronic charges. Now, how do we simulate the quarks? You can either simulate them classically or quantum mechanically, relativistically or non-relativistically, and what effect does it have if we do either of these things? Now, if we treat the quark as an infinitely heavy particle, which is just, so we assume the quark is just like a pollen grain and moving very, very slowly, then how do we calculate some physical observable, which we can then see whether it gives a Brownian-like behavior or not. So then equation of motion of the quark will be just the Newtonian equation of motion, which is just q dot is the force that is acting upon the particle. And then the quantity of interest that we usually have in these systems is the momentum diffusion coefficient kappa, which is the time derivative of this average q square, which is the accumulated q square throughout the evolution of throughout the dynamics of the quark up to some time t. And since q dot is fi, we can actually calculate q dot square from here. So we can integrate q dot square and 2 times, and then we can get q square delta t. And since q dot is q dot is f, so this is just the force correlator, which if in case of color charges also f is proportional to E. So this is just the electric field correlator in color space. And if the kicks, so this essentially represents the kicks of the gluons on the quark, and if these kicks are uncorrelated, which is that this is just the delta function, then this integral just gives you a linear behavior, which is what we get in case of a Brownian motion at late times also, that the average q square, this is called a momentum broadening. This is what is called the momentum broadening. This is linearly, this is proportional to the time interval delta t, and this signifies purely diffusive motion. Now, that is what happens when you treat quarks classically. What happens if you treat them as relativistic particles and quantum mechanically? So then we simulate the dynamics using the Dirac equation, which is the quantum mechanical evolution equation of quarks. But what we see that diffusive regime is still there. So this line that you see. So on the x-axis you have the delta t in terms of q, which is the energy scale of the system, which is 1 GeV, of the order of 1 GeV. And on the y-axis you have the second moment, which was just the average q square that we calculated classically in this one. So you see that in the purely diffusive regime, same for Brownian particles, you have this to be linear to t. Here also you have overall behavior of linear behavior, but there are some oscillations you can see here as well. But there are some oscillations which are related to the which are more than what you expect in a purely Brownian system. So we see that, but one thing to note is that, so what is plotted here are so at different masses, how does this second moment or average q square changes with time, and as you increase mass, it is going down, and this brown one is the E correlator, which is just this one. So essentially treating quark as an infinitely heavy particle. So you see that as you increase mass, it goes to this one, but the corrections are for finite mass is still quite large. So what we see that there are significant corrections for charm and bottom. So m being 1.2 is m is 1.2 GeV, which is the charm mass, and m by q 4.2 is the bottom mass, which are this orange one and this blue one. So we see that the corrections to this average q square are still quite large if you consider them to be a finite mass relativistic quantum particle. So we can say that at least charm is not that much heavy if we are studying the momentum broadening and diffusion of heavy quarks inside gluons. So yes, the answer is yes. Heavy quarks inside a sea of gluons do behave like Brownian particles, but there's more to it than meets the eye, and that's it. That's what I wanted to tell you.
One quick question. I just wonder, can you write down Langevin-like description? Because when you wrote down Q dot equals Fx, like,
Yes.
can you actually have an effective noise term somehow?
Yes. So this is at so this dynamics is was a non-equilibrium dynamics, but here, okay. So this delta t, this force was correlated when we write. This should have been written as proportional because there is some term which is proportional to the temperature of the system, which comes here in the correlator. So which gives us the thermal noise, thermal kicks essentially for the particle to diffuse, basically, which is obtained from the kinetic energy of the molecules. So yeah, so this should not be equal. There should be some thermal term here.